This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today I am going to discuss the register organization of 8086 processor. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals by A.K. Ray and K.M. Budchandi. The publications are Tata McGraw Education. Now we will see the register organization of 8086. In this topic, we are going to see what are the various registers are existing in 8086, the significance of each and every register, along with the classification of registers we will see in detail. 8086 microprocessor has a powerful set of registers known as general purpose and special purpose registers. So the registers which we are having in 8086, basically we are classified into two types. One is a general purpose register, the second one is special purpose registers. All the registers in 8086 are 16-bit size. The general purpose registers can be used either for 8-bit or 16-bit registers. So for 8-bit operation, we can use these registers in 8086 processor. For 8-bit applications, we are going to have total 8 8-bit registers, namely AL-AH, BL-BH, CL-CH and DL-DH. If you are using for 16-bit case, then the registers are named as AX, BX, CX and DX. So with respect to general purpose registers, we can see that 8086 processor is consist of 4 16-bit registers, or we can refer it as 8 8-bit registers. These registers either used for holding the data or variables and intermediate results temporarily or for other purpose like a counter or for sorting effort, offset values of some addressing modes, etc. The special purpose registers are used as segment registers, pointers and index registers, as offset storage registers for particular addressing modes. Now we will see the general purpose registers. The registers AX, BX, CX and DX are the general purpose registers which are existing in 8086 processor as a 16-bit register. The AX register is used as 16-bit accumulator with the lower 8 bits of AX designated as AL and the upper 8 bits as AH. Here the L and H specifies the lower and higher bytes of a register and X indicates it is for 16-bit register. So as we have AX register, that we can split into two 8-bit registers, that is AL and AH. For AH register, which is a 16-bit size, the lower 8 bits we can see in AL register and the upper 8 bits we can see in AH register. For 8-bit application, this we will refer with AL and AH register. The register BX is used as offset storage for forming the physical address in case of certain addressing modes. The CX register is also used as default counter in case of a string manipulation and loop instruction. The DX register is a general purpose register which may be used as an implicit operand or a destination in case of few instruction. When we are referring for 16-bit case, the BX register will be referred as BX register, where the lower 8 bits we are going to be placed in BL register the upper 8 bits we are going to be stored in BH register. If it is for 8-bit operations, we are going to refer the register as BL and BH. Similarly, for CX register, for 16-bit applications, we will refer the register as CX, where the lower 16 bits of the data, lower 8 bits, we are going to be placing CL register, and the upper register for, that is CH, for upper 8 bits. For 8-bit application, we are going to be referred the registers as CL and CH register. Similarly, for DX register, the DX register, the lower 8 bits we can see in DL register, the upper 8 bits we can see in DH register. The next one is, we will say, a special purpose register. All these registers are 16-bit size. We can't divide this one for 8-bit applications. We have to use as a 16-bit registers only. These special purpose registers, we have 3 types. The first one is segment registers. The second type of registers is pointers. The third type of special purpose registers is index registers. As the memory in 8086 processor is divided into some number of segments, for addressing a particular memory, we require a 20-bit address, but we don't have any register for holding 20 bits register in the 16-bit registers. So these 20-bit registers, we are going to be stored in 2 different values. One is a segment register. The second one is offset. By making use of these 2 components, we are going to generate the 20-bit address lines. The segment register usually will consist of the base address or the starting address of a particular segment. In 8086 processor, we have total 4 different types of segments we can have, namely code, data, stack and extra segment. Next one is pointers. These pointers and index registers are mainly used for holding the offset value. Offset value is nothing but the displacement of your target memory location from the starting address or the base address of a segment. How much amount of displacement we are having, this will call as offset. Unlike 8085, 8086 microprocessor, the addresses a segmented memory. The complete 1 MB of memory which the 8086 addresses is divided into 16 logical segments, with each segment have maximum is 24 kilobytes. So as we have 20 address lines, the maximum memory we can address is 2 to the power of 20, which you can write as 2 to the power of 10 into 2 to the power of 10, which you can take as 1k into 1k, which will use 1 MB. So the 1 MB of memory we can use for allocating the entire data or code or stack related for memory. This 1 MB of memory we are going to divide into few number of segments. The maximum allowed segment is 64. So the number of segments allowed are 16. So the size, maximum size of each segment is given as 2 to the power of 20 divided by 16. That I can write as 2 to the power of 20 divided by 16. We can write as 2 to the power of 4, which will use 2 to the power of 20 minus 4, that will use 2 to the power of 16. The 2 to the power of 16 we can write as 2 to the power of 10 into 2 to the power of 6, where 2 2 to the power of 10 is 1k and 2 to the power of 6 is 64k, that will give us 64k. Indicates it is the maximum memory which we can allocate for a particular segment. Now coming to the segment registers, as we said earlier, the segment registers are used for holding the starting address or base address of a particular segment. In 8086 processor, we have total of 4 segment registers, namely code segment register CS, data segment register DS, extra segment register ES, and stack segment register SS. The code segment register is used for addressing a memory location in the code segment of the memory where the executable program is stored. The data segment register points to the data segment of the memory where the data is residing. The extra segment also refers to a segment which essentially is another data segment of the memory. Thus, the extra segment also contains data. This data segment and extra segment, these two segments are used for storing of the data only. But why we require two different segments is, if you are taking a string manipulation instructions, in the string manipulation instruction, if I have two strings for comparison or another purpose, we have to load one string, assume it is S1, we are going to load in one segment. The second string, assume it is S2, we are going to be load into another segment. So as for supporting the string manipulation instructions for storing the source string S1 in one segment, another string in another segment, we have total two segments we have. One is data segment, another one is extra segment. The extra segment, it is mainly used for string manipulation instructions only. The fourth register is the stack segment register, which is used for addressing the stack segment of memory, that is memory which is used to store stack data. So in detail, we have 8086 processor is consist of 4 segment register, namely code segment, data segment, extra segment and stack segment. Code segment will store the starting address or base address of a code segment. Data segment register will hold the starting address or base address of a data segment. Extra segment register will hold the base address or starting address of a extra segment, which is nothing but another data segment. The stack segment register which will hold the base address or starting address of a stack segment. While addressing to any memory location bank in 8086 processor, the physical address is calculated from two parts. The first one is a segment address. The second one is offset. As 8086 processor is consist of 20-bit address lines, but the registers which we are going to have is only 16-bit size. For generating this 20-bit effective address for a particular memory location, we are making use of two register contents. One is the starting address or base address in the segment register. The second one is offset. For providing offset, there are different ways we can use for providing the offset values. That depends upon which addressing mode we are going to use. Next, the segment registers contain a 16-bit base address related to different segments. Any of the pointers and index registers or BX register may contain offset value location of the address. Offset is nothing but the displacement from the starting address to the target location. This offset value either we can store in the pointers or index registers or BX register. Apart from that, in few addressing mode, directly we can specify the offset value in the instruction. The advantage of this, instead of maintaining 20-bit registers for physical addressing. The processor just maintains two 16-bit registers. Thus, the code segment register CS, data segment register DS, stack segment register SS, and extra segment register ES respectively contain the segment address of code, data, stack, and extra segment of the memory respectively. It may be noted that all the segments are logical segments. They may or may not be physically separated. In other words, a single segment may require more than one memory chip, or more than one segment may be accommodated in a single memory chip. The next one is pointers. These pointers are mainly used for holding the offset value, which is nothing but displacement from the starting address to the target location. In 8086 processor, we have 3 pointers. Namely, instruction pointer, base pointer, and stack pointer. These pointers mainly consist of offset value within a particular segment. The pointers, instruction pointer IP, base pointer BP, and the stack pointer SP, usually contain offset within the code segment using instruction pointer, and for stack, either we may use the base pointer or stack pointer. Most of the cases we will use stack pointer only for holding the address for stack memory. The next type of special purpose registers we have is index register. The index registers are used as general purpose registers as well as for offset storage. If you are not using for offset storage, then we can make use as a general purpose registers. In case of indexed, based index, and relative based index addressing modes. In these three addressing mode, the index registers are used for holding the offset value. The register SI is generally used to store offset of the source in the data segment, while the register DI is used to store the offset of the destination in a data or extra segment. So for string manipulation instructions, we are using two segments. One is a data segment, the second one is extra segment. For data segment, we require one pointer. For extra segment also, we require one pointer, but we don't have any pointers for holding the offset value for a data segments. So for that purpose, we are going to use the segment registers SI and DI mainly for string manipulation instruction. For DS, it will be accompanied with SI, whereas ES will be combined with DI for addressing a particular memory location in the data segment or extra segment. The index registers are particularly useful for string manipulation instructions mainly. Next, we have a flag register. The 8086 flag register indicates the result of computation in the ALU and to control the CPU operations. 8086 has a 16-bit flag register, which is divided into two parts. The flags which are existing in this flag are either they may be conditional code or status flags and mission control registers. As the register is consist of 16 bits, but we have only 9 active flags, the remaining bits are don't cares. The conditional code flags register is the lower byte or 16-bit flag register along with the overflow flag. These flags reflect the result of the operation performed by the ALU. The control flag register is the higher byte of the flag register of 8086. It contains mainly three flags. One is direction flag D, interrupt flag I, and the trap flag T. The format for a 16-bit flag register is as shown in figure. LSB is C, it indicates for carry flag. Next bit is X. X indicates here don't care, where we don't have any significance for that particular bit. The next bit is for parity bit P. Next one is X, indicates it is a don't care. Next we have AC, which is auxiliary carry. Next bit is a don't care. The next bit is zero flag. S is for sign flag. T is trap flag. I is interrupt flag. D is direction flag. O is overflow flag. The upper four bits are don't cares. So total we have 9 active flags. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the various active flags existing in 8086 processor are carry flag, parity flag, auxiliary carry, zero flag, sign flag, trap flag, interrupt flag, direction flag, and overflow flag. Wherever in the flag register format, X denotes it is a don't care. The complete bit configuration of 80 flag register is shown in figure. O stands for overflow flag, I is for interrupt flag, S is for sign flag, AC is for auxiliary flag, C is for carry flag, D is for direction flag, T is for trap flag, Z is for zero flag, P is for parity flag, X indicates don't care, and these bits are not used. Now we will see in detailed description of each and every flag, what it is going to signify. The description of the flag bits as follows. The first one we will discuss about the sign flag, where S bit. This flag is set when the result of any computation is negative. When we are performing any operation, if it produces the result is a negative, then the sign flag will be reflected depending upon either the result is positive or negative. The sign flag is equivalent to 1 if the result is negative. Else, that means if the result is a non-negative, then the sign flag is going to be 0. The second flag we are having is Z flag, which is a zero flag. This flag is set if the result of the computation or comparison performed by the previous instruction or instructions is 0. The Z flag will be set to 1 if the result obtained is 0. If the result obtained is non-zero, then the Z flag is going to be 0. The next bit is corresponding to a parity flag P. This flag is set to 1 if the lower byte of the result contain even number of ones. In general, the parity bit indicates how many number of ones are there in your data. Number of ones in the data. There are two types of parities. One is even parity, another one is odd parity. Either any system may use even parity scheme or odd parity scheme. If you are using the even parity scheme, the parity bit is equivalent to 1 if the number of ones in your data is even. And the parity bit is equivalent to 0 if number of ones in the data is odd. When it comes to odd parity scheme, the parity bit is equivalent to 1 if number of ones in your data is odd. And this parity bit is equivalent to 0 if number of ones in your data is even. In 8086 processor, the 8086 processor, it is going to follow even parity scheme. That's why if the number of ones in our data is even, the parity bit will be 1. So if the number of ones in our data is even, the parity bit is equivalent to 1. Else the parity bit is equivalent to 0. That indicates number of ones in your data is odd. The next one is a carry flag. See, this flag is set when there is a carry out of MSB in the case of addition or a borrow in case of subtraction. So when you are doing the addition or subtraction, if any carry is generated in the MSB position or if any borrow is taken in the MSB position, then this carry flag will be affected. So if any borrow or any carry is taken in the MSB position, then the carry flag is going to be 1. Suppose if no carry is generated or no borrow is taken in the MSB position, in that case, the carry flag is equivalent to 0. The next flag is trap flag T, which is a mission control flag. If this flag is set, the processor enter into a single step execution mode. That is, the trap interrupt is generated after execution of each and every instruction. So once the trap flag is 1, then the processor will start executing instruction 1. Once the execution is started, immediately the trap flag will become 0. At the end of the execution, again the processor will make the trap flag is equivalent to 1 so that it can execute for further instruction. If trap flag is equivalent to 0, the execution will not be starts. So the trap flag will be generated after execution of each instruction to execute the next instruction. Out of all the interrupts, trap is having highest priority in 8086 processor. The processor execute the current instruction and the control is transferred to the trap interrupt service routine. The next bit corresponding to interrupt flag I. If this flag is set, it indicates there is a maskable interrupt that will be recognized by the CPU. If the processor interrupt is not generated, then it will be ignored. So the presence of interrupt we can see on I is equivalent to 1. The next one is corresponding to the direction flag. The direction flag is mainly used for string manipulation instruction. If I have a string S1, so which is consist of some elements, let us consider X1, X2, X3, X4. How we want to process this string? Either from X1 to X4 or X4 to X1. This direction of manipulating of the string will be takes place depending upon the direction flag bit. If direction flag is equivalent to 0, the string is processed from the beginning to the lower address to higher address. That is from X1 to X4 in this example, because this X1 is at a lower address and X4 is at higher address. So when the direction flag is equivalent to 0, the execution will be take place or the string manipulation instruction will be executed from the lower address to higher address. If direction flag is set to 1, in that case, the string is processed from higher address to lower address. If the direction flag is equivalent to 1, the string manipulation will be starts at higher address and it will end at lower address. For every string manipulation instruction, automatically the incrementing or decrementing will be takes place depending upon the direction flag. If you use the direction flag and it is reset, in that case the offset value will be go for automatic incrementing. Usually for a source register SI will be incremented, for destination string DI will be incremented. If the direction flag is set, automatic decrement will be takes place. After every string manipulation instruction, automatically the corresponding index registers is going to be decremented. Either the decrement will be 1 or 2, depends upon what is the string size. If the string is 8-bit size, the auto increment or auto decrement will be takes place by 1. If the data is 16-bit size for each and every string element, in that case, the auto increment or auto increment will be takes place by 2. The next flag is auxiliary flag. That is auxiliary carry flag, AAC. This auxiliary flag will set if there is any carry or borrow in the lower nibble. That means bit 3 to bit 4 during addition, borrow bit 4 to bit 3 in subtraction. So out of the data, either it may be the 8-bit data or 16-bit data, only the auxiliary carry flag will be affected if there is any borrow or carry generated in the lower nibble, that is lower 4 bits. If any carry is generated or borrow is broken in the lower nibble case, in that case the auxiliary flag will become 1. So auxiliary flag is equivalent to 1. What it indicates is if any carry or borrow in the lower nibble position. The auxiliary carry is equivalent to 0 if no carry or no borrow in the lower nibble position. The next flag is overflow flag. This overflow flag is set if an overflow occur. That is, if the result of a signed operation is larger than or it is large to accommodate in a destination register. The overflow flag is equivalent to 1. It signifies a overflow is occurred. If overflow flag is equivalent to 0, it indicates there is no overflow occurring. So in this session, we have discussed the various flags as well as registers which are existing in 8086 processor. In 8086 processor, there are mainly two types of registers. One is a general purpose register. The second one is special purpose register. Under general purpose registers, we have 4 16-bit registers which also used for 8-bit operation. In that case, we have total 8 8-bit registers. For 4 registers in 16-bit case, namely AX, BX, CX and DX. For 8-bit operations, we will take that registers as AL, AH, BL, BH, CL, CH and DL, DH. The second category of the registers of 8086 processor are special purpose registers. Under this, we have 3 registers: segment registers, pointers and index registers. Segment registers are used for storing the base or starting address of a particular segment. The segment registers we have 4 in number: code segment register, data segment register, stack segment register and extra segment register. The code segment register will hold the starting address or base address of a code segment. Data segment register will hold the starting address or base address of a data segment. Extra segment will hold the starting address or base address of a extra segment. The fourth one is stack segment register, which will hold the starting address or base address of a stack segment. The next type of special purpose registers are pointers and index registers. These are used for mainly holding the offset value for a particular segment. Under pointers, we have total 3 pointers, namely instruction pointer IP, base pointer BP, stack pointer SP. For data segment, we are going to use the index registers for holding the offset value, or BX register, or in the instruction will be specified the offset value in few addressing modes. The next type of registers we have discussed is flag registers. Apart from general purpose, special purpose, we have another register which is a flag register, which is going to reflect the result of the ALU. For that, we have few status flags. Apart from that, few flags are there for controlling of the processor. The flag register of 8086 processor, which is a 16-bit size, out of which 9 active flags are there. The various flags which are existing are 0 flag, sign flag, auxiliary carry, direction flag, interrupt flag, trap flag, overflow flag, and auxiliary carry. These are the various flags which are existing. 0, sign, carry flag, auxiliary carry, overflow flag, these are status flags. The trap flag, interrupt flag, and data direction flag, these are mission control flags we are having. So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.